Assalamualaikum warahmatullahi wabarakatuh and very good afternoon. Today we will be going to discuss about the last chapter under this course, Computer Architecture Organization, which is under topic 8, Computer Performance and Evaluation. So thank you for your participation. Thank you for your commitment so far. Thank you for your attention for my class and all the questions that you have sent to me. And today will be the final chapter, and there will be only one video for the lecture, and there will be another one for the lab. And for this one, it will be a short one, okay? And thank you for your commitment so far until end of the semester. We have 8 chapters and more than 30 videos already. So thank you for your commitment, and I hope you guys can success in your final assessment, especially for UMP students. Okay, so without further ado, let's start our class. So under computer performance evaluation, the outline of the topic itself is we have 4 things that we'll focus in to, which is computer performance evaluation, performance definition, cycle per instruction, and also AMDAHL'S law. So what exactly performance mean? So performance basically means response time, which is derived by a simulation program finished within 5 minutes. So this is what we call a response time. Or it can be categorized by throughput. Example is that a web server serves 5 million requests per second, or any other metrics, like for example, we have million instruction per second, how many million of instruction can process per 1 second. And we have MFLOPS, which is mega floating points operation per second, means that how many floating point operations can be conducted within 1 second. This one is common measure of the speed of computer used to perform the floating points calculation. And we have also the most common thing that we use even when we want to buy a new computer is the clock frequency. How many hertz does it have? Okay. So basically for execution time, okay, so processor design is concerned with processor consumed by program execution. Means that the shorter execution time it has, the better the PC is, the processor is. So means that with shorter execution time, you can get shorter response time and higher throughput. So execution time is basically the number of instruction here times with the number of cycle per instruction, means the clock cycle per instruction, and it's time the clock cycle time itself. Okay, so clock, they have the cycle which commonly derived by the tick tock of the clock, and the cycle time is when it start to ticks and it ended with tocks. So tick tocks one cycle time, okay, how long it takes. So cycle per instruction means that how many tick tocks per instruction and how many number of instruction has to execute a program. So what affects the number of instruction? The CPI, which is clock per instruction, and cycle time. So through this method, almost all designs can be interpreted whether it's better or bad. Okay, so any other metrics is meaningful only if consistent with the execution time. So how do you actually evaluate the performance of computer? So performance is defined for a program and a machine. So sometimes we use it based on real application, like for example, scientific program, compilers, text processing, software image processing, and sometimes even game. Okay, and then we have modified application, like for example, providing portability and focus. Sometimes we compare according to the kernels. So this one is usually happening with using Linux kernels, and which is good to isolate the performance of individual features. Okay, so one of them you can measure latency and bandwidth of the memory and file system networking, etc. So we also can do based on toy benchmark and also synthetic benchmark. So which is matching the average execution profile among other computers and other processors as well. So this is how actually you compare the computers with this kind of what we call a benchmark. So if you know what do we need to do when we compare computers, okay. So if you commonly watch any videos that review computers in the YouTube, sometimes they review graphic cards depending on how good it is to play certain game. Like recently we have the game Cyberpunk 2077, right? So this one, people compare the performance of AMD Radeon processors and also NVIDIA RTX processors, so to compare which one is a better graphics. So they use the game as a benchmark, which is one of the real applications that we have in current stage, which is the latest one. So when we want to compare a performance between two devices, usually you came out this kind of terms. X is n times faster than y is n times slower than x. So this kind of x is n times faster than y means that what actually that you define the x and n and also y. Okay, so how do you define them? So basically, performance of x comparing to performance of y is equal to the execution time of y divided by execution time of x. And through this, you will get the n. Means that this is where you have, like for example, x is 2 times faster than y, or x is 2 times lower than y, okay? So this is where you can see the performance actually. So when you look at, okay, the speed up, okay, n is basically is the speed up if we are considering an enhancement optimization for PC Y, which is you create a new PC of X. So what does improving mean actually? So improving means that they improve performance, which is decreasing execution time by increasing throughput, okay, and then or even increasing throughput without influencing the execution time. And then we have improved the execution time or decrease the by decreasing the execution time, and we degrade the performance, okay, which is the reverse of the above, means that by bring negative speed up. So this one is means that you degrade the performance of the PC of you are comparing, so that you can see that your PC is better than the negative speed up PC, okay. So we have this benchmark suit that we use to compare. Okay, so what exactly the benchmark suite? So benchmark suite is a collection of benchmarks with a variety of applications. So this one, alleviating weakness of a single benchmark, more representative for computer design to evaluate the design, and benchmark test both computers and compilers and OS in many cases. So usually our desktop benchmark is the CPU, memory, and graphics performance. And the server benchmark, usually the throughput oriented I/O, which is involving the I/O input and output of the server, and also the OS intensive. And also we have, other than that, is the embedded benchmarks, which measuring the ability to meet deadline and save power. So in terms of summarizing the performance, okay, I'm giving you here a set of PC, okay, ABC PC with programs running, program 1 and program 2. So you look at these images, which PC that you think is the best one, okay? So which computer is the best one? So you have program 1 for PCA is runs under 1 second, but program 2 takes 1000 seconds. However, program B is for PCB, program 1 is 10 seconds and program 2 is 100 seconds. For C is program 1 is 20 seconds and program 2 is 20 seconds. So which one do you think is the best one? So most of you might think of C would be the best one, since overall of the total took only 40 seconds. So it's somehow correct. So what exactly is performance? So when we want to understand performance, so Performance, usually they involve four things, which is algorithm, programming language, compiler architecture, and processor and memory system, and also I/O, okay, including the OS. So algorithm, which determines number of operation executed. Programming language, compiler architecture determine number of machine instructions executed per operation, and processor and memory system determine how fast instructions are executed, and I/O system determine how fast I/O operations are executed. So we have the response time and throughput, which I mentioned before. So response time is we use to evaluate how long it takes to do a task, means that shorter is better basically. Throughput is how many work can it do within a unit of time, means how many work you can complete within 1 hour. Okay, so this is also one thing that we look at when we evaluate performance. So how are response time and throughput affected by replacing the processor with a faster version or adding more processor? So this is where it involves. So we focus on the response time for now. So when we look at response times, okay, so define performance is equal to basically 1 over execution time. Okay, so if x is n times faster than y, performance x divided by performance y equal to execution time y divided by execution time x, which is equal to n. So this n is how many times faster the x between the y. So example here is that it takes 10 seconds on A and 15 seconds on B. So execution time B, which is 15 seconds, divided by execution time A, which is 10 seconds, equal 1.5. So A is basically 1.5 times faster than B. So next, we have 60 seconds on A, 30 seconds on B. So execution time B divided by execution time A equal to 30 seconds divided by 60 seconds, which is 0.5. So A is 0.5 times faster than B. Means, another word, if you change it around, is that B is basically 2 times faster than A, because A is half time faster than B. Okay, so B is 2 times faster than A. So when we want to measure the execution times, okay, basically we measure according to the elapsed time, okay, which is the total response time, including all aspects, okay, which is the processing, I/O, OS overhead, idle time, and also it determines the system performance itself. And next we have the CPU time. So CPU time is the time spent processing a given job, which is the like for example discounts the I/O time, okay, and other job shares. And also it comprises user CPU time and system CPU time as well. So different programs are affected differently by the CPU and the system performance. So that's why CPU time might vary according to the program. So if you see that, okay, in the CPU we have a clock. So operation of digital hardware governed by a constant rate clock. So if your CPU is a fast clock, like 4 gigahertz, it's much more faster for it to operate instruction based on 2 gigahertz CPU. Why? Because our instruction is processed based on the clock rate. Okay, so if you see that here, clock cycle, and here is the data transfer and computation, and here is the update state. So clock period or clock cycle time is the duration of a clock cycle. Okay, duration of the clock cycle. And for each clock cycle, okay, instruction is being conducted. Sometimes it takes more than one clock cycle, but instruction is being conducted during this period. So clock frequency is basically how many cycles per second, means that how many ticks and talks it has per second. Okay, this is one of the important things that you have, and your PC CPU is determined by this. Okay, clock frequency, cycles per instruction. So when you talk about CPU time, okay, CPU times is basically the CPU clock cycles time clock cycle time. Okay, so or it equal to CPU clock cycle divided by clock rate. So performance is improved by reducing the number of clock cycles or increasing the clock rate. And hardware designer must often trade off the clock rate against the clock count to make sure that the performance is optimum. So basically that we have these days is that we less look at the clock frequency these days, because more they try to create a CPU with more cores inside. So when you have more core inside, it's better for you to distribute the instruction to be processed among cores that you have inside your CPU, rather than one core only that process everything. So rather than you increase the processor clock rate, usually they have a limitation for them to increase up until the end. So in order to improve the performance of your PC, they add another core so that they can distribute the task between two core with the same clock rate. So example here, computer A, 2 GHz clock you have here, and 10-second CPU time. So you want to design a computer B, aim for 6-second CPU time. Okay, it can do a faster clock, but it causes 1.2 times clock cycle. Okay, how fast must clock be? Clock B. So this one is the clock rate. So clock rate B is equal to clock cycles B divided by CPU time B. So you have here 1.2 times clock cycle A, okay, because we want the number of clock cycles involved, okay, is 1.2 times the clock cycles from A divided by 6 seconds. So clock cycle is equal to CPU time A times clock rate A equal to 10 seconds times 2 gigahertz equal to 20 times 10 power of 9. So clock rate B is 1.2 times 20 times 10 power of 9 divided by 6 seconds equal to 24 times 10 power of 9 divided by 6 seconds equal 4 gigahertz. Okay, so basically in order for you to have a 6-second CPU time, okay, with 1.2 times longer clock cycles, you can have a 4 gigahertz CPU. So next we go towards instruction count and CPI. So clock cycles is basically the instruction count times cycles per instruction. Okay, instruction count times cycles per instruction. So how many clock cycle per instruction times the instruction count it need to complete a certain program. And the CPU time is the time it takes to process everything. Okay, which is equal to instruction count times CPI, cycle per instruction itself, times clock cycle time, which is equal to instruction count times CPI divided by clock rate. So instruction count for a program, okay, determined by program, okay, ISA and a compiler. Average cycle per instruction determined by the CPU hardware. If different instructions have different CPI, average CPI affected by the instruction mix. So I'll give you an example here. Computer A, cycle time 250 picosecond, CPI 2.0. Computer B, cycle time 500 picosecond, and CPI 1.2. Okay, it's the same ISA, means that the same form factor, and which is faster and by how much. So CPU time A is equal to instruction count time CPI A times cycle time A. So you imagine here the instruction is 1. For one instruction, okay, it took for uh, okay, 1 times 500 picosecond. So instruction count times CPIB times its cycle time B, you got 1 times 1.2 times 500 picosecond equal to 1 times 600 picosecond. So CPU time A time CPU time B divided by CPU time A is equal 1 times 600 picosecond divided 1 times 500 picosecond. Okay, you can see that you can remove the 1 here, and you got it 1.2 times faster. Okay, so in this case, okay, how much faster does the CPU A compared to the CPU B? So CPU A is 1.2 times faster than CPU B. So CPI, okay, if you look at into the more detail, if different instruction types take different number of cycles, okay, so here we have what we call a weight average CPI. Okay, so CPI times instruction count I divided by the instruction count. So we have this one is the average CPI that the computer have. So other than that, we have this in this case is alternative compile code sequence using the instruction in type of integer, FP and N. So CPI for type, this one is 1, FP floating point, here 2, this one is for memory, it's 3. And here is the instruction count. IC goes for instruction count in program 1, instruction count for program 1 for all of them. And here is instruction count for program 2. So in this case, in case program 1 instruction count is 5. Okay, clock cycles equal to 2 times 1, 1 times 2, and 2 times 3. Okay, so here is this one. You can see that here 2 times 1, 1 times 2, 2 times 3. You got 10 for program 1. So average CPI is 10 divided by 5. You have 5 instruction count here, which is 2.0. Okay, for program 2, average CPI is 1.5. So when we look at the performance, okay, CPU time is equal to instruction per program times clock cycle per instruction times seconds divided by clock cycle. So this performance depends on the algorithm which affect the instruction count, possibly the CPI itself, and also programming language which affects the instruction count and also CPI. Compiler affects the instruction count and CPI, and instruction set architecture which is affect the instruction count, CPI, and also the time. And if you look at this is a graph that is showing a power trends. Okay, so this is another way for us to evaluate the performance itself. Okay, so if you look at the black line here, the number of watts it takes, okay, to improve the clock rate. Okay, and here you see that the higher the clock rate is, the more power it consumes. So power is equal to capacitive load times voltage power square times frequency. Okay, so this one in this case, okay, power is times 30. Okay, capacitive load and voltage is actually 5 volt to 1 volt, and frequency is 1000. See, this one is just one example. So in case we want to reduce power, okay, suppose a new CPU has 85% of capacitive load of old CPU, 50% voltage, and 50% frequency reduction. So this is a power of new and versus power of old. So this one you have capacitive load 0.5 for the new, 0.85, voltage is 0.85, and for frequency 0.85. So you see that the total is 0.85 power 4 you can get is 0.52. Okay, so the difference between the power for new and old is almost 50%. Okay, 50% reduction. So okay, so actually for us to reduce the power for the decrease performed by power for the CPU, okay, we have what we call the power wall. Okay, so we cannot reduce the voltage until a certain point. Okay, and then we cannot remove more heat. Because we cannot remove more heat, we cannot reduce the voltage further. We cannot remove more. If actually we can increase the voltage, but we cannot remove those heat that created by those voltage, which is also another problem inside the PC if you want to increase the performance through the power. Okay, so for this case, okay, basically cost performance is improving due to the underlying technology development, hierarchical layers of abstraction in both hardware and software, instruction set architecture, the hardware and the software interface, execution time is the both performance measure, and power is a limiting factor. Okay, so that's why a lot of performance maker right now, they use a parallelism to improve performance. Means that they use a lot of cost to increase performance, because you cannot increase the frequency anymore because of the limitation from the power itself. Okay, next, we're going to introduce you the AMDAHL'S law. Okay, AMDAHL'S law is basically named after computer architect Jean AMDAHL. So they used to find the maximum expected improvement to an overall system when only part of the system is improved. So AMDAHL'S law can be interpreted more technically, but in simplest test, it means that it is the algorithm that decides the speed up, not the number of processors. So AMDAHL'S law, okay, is a demonstration of the law of diminishing return. So while one could speed up part of a computer 100 times fold or more, if the improvement only affects 12% of the overall task, the best speed up could possibly be is 1 divided by 1 over 1 minus 0.12, which is the 12% here. 1 subtract the original time, subtract with 0.12, which basically you only get 1.136 times faster. Okay, so more technically, the law is concerned with the speed up achievable from an improvement to a computation that affects a proportion of proportion P of that computation, where the improvement has a speed up of S. So basically, looks like this. Okay, for example, if an improvement can speed up 30% of the computation P, okay, computation P will be 0.3. If the improvement makes the portion affected twice as fast, S will be 2. Okay, AMDAHL'S law stated that the overall speed up of applying the improvement will be look like this. So how actually you use this formula? Okay, so okay, let's skip that one. Here is an example. We are given a task which is split up into 4 parts. So you have program 1, 2, 3, 4, 5. So each of them, okay, you have the original one is 11, 18, 23, 48, which add up 100% of all the programming time. Then we say that on the program, part 1 is not sped up. Okay, means that is original one. Part 2 is 5 times sped up. Part 3 is 20 times sped up. And part 4 is 1.6 times sped up. So when you want to calculate them, the overall running time of your program, okay, so you have, based on this formula, you have the 11% divided by 1, okay, because it's not sped up, okay, and then 18% 5 times, 23% 20 times, and 48% is 1.6 times. Okay, when you find out the running time according to this formula, you get 0.4575, or a little less than half the original running time, which we know is 1. Therefore, the overall speed boost is 1 over 0.4575, which is equal to 2.186. Okay, so based on this formula. This one is based on this formula. So if you look back at the top here, even though some part they increase up to 20 times fold, so the overall improvement of the program, the algorithm itself, is basically only 2 times. Okay, so that's all for me for chapter 9 and chapter 8 here. So I wish you good luck for your assessment later on, and look forward for the lab explanation. I will post in the next 2 days. So because this is a short short chapter, so finish it quick, and next week you can just focus on your finals. So I'll see you guys later on. Hopefully, okay, you can stay safe, stay healthy, and take care. Assalamualaikum and good day.